exploit development by looking at a slightly different kind of exploit. We've worked with saved return pointer overwrites for all of this module, so let's take a look at something called a structured exception handler overwrite. This is going to be Windows specific. Structured exception handlers are how Windows deals with errors in the program. So when an error occurs, execution is passed to the structured exception handler, which is basically a linked list of 8-byte structures. So we have the address, or a pointer to the next link in the chain, if you will, the next structured exception handler entry, and then the address of the structured exception handler itself. So if the first one can't process the exception, it moves to the next one, and so on. And then finally we have the last one, which has all F's as the address of the next one. There is no next one, and then we're at the end. So you've probably seen the default operating system one, it being the program has encountered an error and needs to close. But developers can add their own structured exception handlers if they like. So let's see how we can use structured exception handlers to get control of a program. So we're again going to look at warftp. So I have warftp scale2.py that is included with the course as well. So it's another exploit skeleton. So very similar to what we had previously, except instead of 1,100 A's, this time we have 1,200 A's. So what happens if we make our attack string a little longer, and we do need to change our IP address to your Windows XP system. Otherwise, this is exactly the same as our regular warftp skeleton that we did earlier in this section. So you should be familiar with it. It is sending a long username and causing a buffer overflow condition. So of course, in this case, we already have a saved return pointer overwrite that works, but you may find yourself in many situations where you only have the structured exception handler as a way of gaining exploitability, or even getting a crash in the first place. So this is definitely worth knowing for Windows exploitation. So let's go ahead and save this. Hop over to XP and start up warftp. I need to delete my ftpdaemon.dat. Start up warftp. Start. Community debugger. Attach to warftp. And click play. We should be good to go here. Alright, let's go ahead and run this. Make it executable, chmod +x, and then run it. See the same output here, so everything looks normal. But if we pop over here, we are crashed, we are paused. It says we got an access violation when writing to 00B0 0000. If we look at EIP, it's a valid address in MSV CRT. We do not have EIP control. So we crashed it, but we don't have control of EIP. So this looks pretty non-exploitable to me. Denial of service is something, but it's certainly not as good as code execution. We take a look at our stack here. See our A's down at the bottom, and it looks like the end of our stack, 00AFFFC. So that'll have FD, E, and F as well, and it looks like we're trying to write to 00B00000. So this would basically loop around, and that would be the next address on the stack. If there was one, it looks like we're trying to write off the end of the stack, which is a good way to cause an exception. So let's see, is there any hope for us at all? Well, the name of the section is Structured Exception Handlers, so that should give you some clue. If we go to View and SEH chain, look at our Structured Exception Handler chains. We've got our address here, and then, so the next address has also been overwritten with A's, and then the Structured Exception Handler 41, 41, 41, 41. So we've overwritten the structured exception handler. So recall that if the program crashes, it will pass execution to the structured exception handler. If we were outside of the debugger, that would just happen automatically. But because we're in the debugger, we're crashed and we have a chance to see what's going on here. And it says use Shift F7, F8, F9 to pass the exception to the program. We want to do Shift F9 to tell it to completely pass the exception. So if you're on Mac, you might have to do function Shift F9. And look what happens. Access violation when executing 41, 41, 41, 41. We passed the exception, and since the exception handler was overwritten by 41, 41, 41, 41, we once again have EIP control. And again, this would happen automatically outside of the debugger. The user's not going to have to do Shift F9 to make this happen. Out of the debugger, it would just be seamless. So as long as we're able to create some sort of crash, we will pass controls to the exception handler. So if we can gain control of it, then we should still be able to get execution. So that kind of puts us back in the same place where we were previously. We need to find out which A's are those that are overriding this time the structured exception handler. So we know how to deal with that. We do a exclamation point Mona and then pattern underscore create. This time we want 1200 A's. Well, not 1200 A's, 1200 bytes of our pattern. So we let Mona create that pattern. And we want to go to C, logs, war FTP, and we have a new pattern. Big. Why is it so big? Alright, so let's grab our pattern and put it into our exploit. While we're here, we can go ahead and restart. So I need to get rid of my evil database file. Go. So again, we can restart this directly in the debugger. Let's go back to war FTP scale 2. Comment out buffer equals A times 1200 and set buffer equal to, with quotations around it, our cyclic pattern. That's the only change we need to make here. Go ahead and run it. Same output here. Looks good. We get our same access violation here, but if we look at the SEH chain again, it's once again overwritten, so the corrupt entry should tell you that that's not a valid address there. And then we have part of the pattern. So we can do our Mona find MSP. And this time, instead of being interested in our registers in particular, we're going to be interested in what's in the structured exception handler. So this will, again, take a little bit of time. It is searching through all of memory. Alright, so let's take a look. Let's just open a second one here. We want C, logs, or FTPD, and then we want our find MSP. And it's huge. And let's see, so we've got SEH record, next SEH field. It's that address overwritten with normal pattern, offset 569. So 569 bytes in, followed by 612 bytes of cyclic data after the handler. So we have offset 569, so then we'll have 4 bytes of the structured exception handler itself, and then after that we have 612 bytes possibly to work with. Well, we can easily verify this, so we say that the offset is 569 bytes in, so let's see if that's true. Doesn't look like. Says we have control of the EBX register, but only 11 bytes after it. As it turns out, that won't be remotely relevant because our registers will actually get zeroed out when we pass the exception. So just jumping to a register isn't going to work here. We'll have to do things a little bit more interesting. So we won't just be able to jump to a register here because they'll be zeroed out. So let's go ahead and verify that offset. So again, that is SEH record offset 569. So let's restart. Alright, so again, comment out our buffer variable, and let's say buffer equals A times 569 plus B times 4, and then buffer plus equals C times 1200 minus the length of buffer. Again, saving ourselves the trouble of the arithmetic. If we don't pad this, then we won't get the exception. Remember, we are writing off the end of the stack, so we have to make sure our string is long enough to make that happen. So in some cases, you may just be able to drop off the end of your string. As long as you've got, say, the save return pointer overwrite, you may be able to drop off whatever comes after. But in this case, it's very important that we have enough bytes to write off the end of the stack, or else we'll lose this crash, so we won't pass to the structured exception handler. Alright, so let's verify this. Same output here. We get the same access violation here, writing off the end of the stack. We view our SEH chain. We have 42, 42, 42, 42 in SEH are the next structured exception handler, so the pointer to the next part. And then we have 43, 43, 43, 43 should be our first four C's rather in SEH itself. So we can pass it, we can do Shift F9, and we get an access violation while executing our first four C's. Alright, so we have verified the offsets. Again, we do have 8 bytes to work with. We have in SEH and then SEH itself. So we actually need to put whatever we want to be executed, whatever memory address we want there in SEH. So we need it to be in place of those first 4 C's. And this is going to be true every time. Structured exception handler entries are always 8 bytes long in SEH, the next pointer to the next one, and then SEH itself right afterwards. That's just how structured exception handlers work. Alright, so let's go ahead and see what we can do here. So again, we lost the one register we did control with all of 11 bytes that we had control of. It has been zeroed out. So we don't have control of any of our registers. We can't just jump to anything. So we're going to have to be a little bit more sneaky. So if we actually look at our stack here, nothing interesting at ESP, of course. ESP plus 4, nothing interesting here. But at ESP plus 8, it looks like we have control here, and also, farther down, it looks like it's here as well. And here, here, and here. So we have our B's, which again is in SEH, and then we have our C's. So it looks like it's a pointer to in SEH right there at ESP plus 8. So if we could find a way to get to that, again, this is going to be the same every time. That's what makes it exploitable, is that every time when you pass the exception, you will end up with in SEH at ESP+8. If you know anything about exploit development, you've probably heard the term pop-pop-ret. This is what that is about. And what we're going to do is pop this line off the stack, pop this line off the stack. We don't care where they go as long as they get burned off the stack, and ESP+8 becomes the top of the stack, and then we can return to it. So that will say, execute whatever is at this memory address, and the instructions at that memory address are going to be NSEH, SEH, and then whatever comes after. So we have our B's and our C's. So, can we do that? Well, we'd have to find pop-pop-rets and equivalent. Luckily, Mona can do that for us. So, we do a Mona SEH, and we can tell it CPB to get rid of the bad characters. Again, those are 0, 0 which for null, and 0A, 0D for hitting enter, and 40 for the @ symbol in the username. We can have it automatically throw those out. So this is just like the jump pretty much, except it's looking for, this time, a series of pointers. We pop, pop, and ret. And again, it doesn't matter what register the pop goes to, we just want to burn those two lines off the stack. So that gives us some more options, since we can take any register for the pop. Alright, so if we take a look at the output of SEH, I don't know why this stuff is so big. Let's make it smaller. Let's say 12. Alright, that's more reasonable. Alright, so we've got our pop-pop-rets here. We just have one little problem. Remember I mentioned safe SEH. Well, when people started actually exploiting structured exception handlers, people got the idea, well, maybe we should make this a little bit harder, and safe SEH was born. And it actually does come into play on our Windows XP Service Pack 3. It did come starting with, I believe, XP Service Pack 2. So we do see that Safe SEH is on for all of our operating system DLLs. It's not on for WarFTP itself and its DLL. So Safe SEH is basically going to record the correct locations of the structured exception handlers. So when we try and overwrite them, if they're not basically in the table it says these are the valid ones, then it will fail. Getting around, there are other ways of getting around Safe SEH rather than just using a module that doesn't use it, but that's the best way. And that's what we'll do here. So again, WarFTPD itself, we ran into this previously, it has a null byte in all of its pointers. It is loaded at null at the beginning, so we're not going to be able to use any pointers from there. We're going to be stuck with just this one mfc42.dll. It's the only safe SEH pointer that's not going to have null bytes in it. Mona automatically takes that into account. It threw out all our bad characters and also throws out anything that comes from a safe SEH compiled module. So everything on this list is going to be from mfc42.dll. So we can just grab the first one here. You don't have to worry about the ret4, and should probably be ret8 down here. So that's, again, with the calling convention, that's just ripping off additional lines in addition to returning. So we saw in the previous one with WarFTP, it had the return address, then 4 bytes of padding, and then ESP, so it was like there was an extra line. So that would be that ret4. It would return, and then it would also rip off the argument. So again, that's a calling convention. It just depends really on the compiler and platform that you use, what it does in terms of dealing with arguments. So we don't have to worry about that at all, as long as we end up returning to ESP+8. We'll pop a line off, pop another line off, and then return. So again, let's just grab the first one. And while we're here, we can restart. Okay. Looks good. Wrong way. Alright. So remember we put our SEH overwrite right after the B's. The B's are in SEH, and SEH itself was overwritten with the first 4 C's. So in little Indian format, we can put our pointer. That didn't work out so well. So we still have the pattern. Let's try that one more time. So SEH, edit, copy. And edit, paste. There, that's better. Alright, so plus, now we need to put this in little Indian format, so CA first, then 80, then 45, and then 5F. And be sure and get rid of this. So again, that's going to go into SEH, so that is going to tell it to do the pop pop ret after we pass the exception. So this is kind of like jump to a register. It's just a little bit more complicated. Instead of just doing a jump, we're popping 2 things off the stack and then returning to it to get to SEH. Alright, so let's go ahead and save this. And run it. Well, yeah, let's run it. Don't have to worry about setting the breakpoint at this point because it's going to crash first and pause anyway, so we can just set it on the fly. Same error, URSEH chain. Now it is a valid address, so we do need to set a breakpoint. What we can do is hit F2 when it's highlighted. It'll turn red. That means the breakpoint is set. So then when we pass it with Shift F9, we pause. Again, now it's a valid address, so it won't crash. So we see in our CPU window, pop, pop, and then ret. So if we go to ESP plus 8 here, and if we say follow it in the stack, there's our 4 B's. So it still points to SEH followed by SEH. You can already see the problem here. We've got 4 bytes to work with before we run into the pop pop ret itself. We've got all this nice space over here. I think it said there were 600 and some, right? Links. Yeah, 612. So 612 bytes to work with for shellcode. Awesome, but we don't really have any way to get there at this point. But one thing at a time. Alright, so let's do our F7s to do our pop pop ret. Let's go back to ESP, so follow ESP in the stack so we can watch these 2 lines be burned off. So watch your stack as we do F7. So pop into EBX. Again, we don't really care where it goes, so that pops 1 line off. Pop EBP, pop another line off, and then we return. And now we see in the CPU window we do have our 4 B's, and then we have our, well, it's trying to turn this into opcodes for our address of our pop pop ret. And then we have, again, all that nice space for shellcode that we can't use until we can get there. So what could we possibly do in terms of shellcode in 4 bytes? Not very much in 4 bytes, but there is one thing we can do, and it's called a short jump. And as the name implies, it allows us to jump a short distance. Well, we want to jump 8 bytes. We want to jump from here to here. That seems doable in a short distance, right? Well, it needs to be able to be done in 4 bytes. Luckily, it can be done in 2, so that's good. Let's try that. Alright, so let's restart. Alright, so this is going to go in place of our SEH. So we need a short jump, which the opcode for that is EB in hex, and then the length to jump. So we can get that from Metasm as well. If I open up another terminal and go to user share Metasploit dash framework and tools, open up metasm underscore shell.rb. We used this previously when we were trying to move ESP out of the way of our decoder in our other WarFTP example with the save return pointer. So this time we want to do a jump. Let's see, so we want to jump from here, so that's going to be $, and we want to jump 8 bytes. So from the beginning of NSEH, we want to jump 8 bytes, so over NSEH and over SEH. So from here, jump 8 bytes forward. So that is EB06, so from the end of the opcode, 6 bytes. So there's 2 bytes left over, and then the 4 bytes of SEH. So it's EB06. You'll come to just remember that. You know, you'll do this over and over again if you work with structured exception handlers. And there are cases where, like, EB is a bad character or something, so you have to work a little bit harder. It certainly can get more complicated, but, you know, just the basic example, we would just do this over and over. Alright, so that will jump us past SEH, so we need to change this B times 4 to B times 2 since we took up 2 of the bytes there. That's the only change we need to make here, is to add that short jump and keep 2 bytes of padding in, so our SEH pop pop ret will be in the right place. Go ahead and run it. And go to SEH chain and set our breakpoint with F2. Pass it with Shift F9. F7, F7, F7. Now we have our short jump. So if we do an F7 on that, it takes us right after SEH. So now we have 612 bytes to work with for shellcode. Awesome. Very, very awesome. It looks like we've gotten ourselves out of the woods here. So we can just put in our shellcode, of course. We could even just copy the shellcode that we used previously in the first WarFTP module. So we just need to make sure we have all of the right bad characters. Alright, go ahead and restart. And let's actually do that. Let's take WarFTP scale.py. Oh, it's actually not there anymore. I deleted it. Alright, so let's do msfbinom and payload Windows shell. Let's say reverse TCP this time. And again, it is inline, so we can just use netcat. We don't have to set up a Metasploit handler. We are going to have to set lhost equal to IP address of Cali, which I believe is 77. Let me check that. Exit config. Yep, 77. So just let the L port default to 4444. Size, I think it said I have 617 bytes. Bad characters, null, 0A, 0D. And again, there is a blog post at bulbsecurity.com that shows how to find bad characters. It's a bit tedious. It's my least favorite part of exploit development, in fact. But it's worth knowing if you want to continue. So I encourage you to look at that blog post. And format is Python. Alright, we don't have to worry about moving ESP out of the way here. Chicago and I will work just fine. ESP is going to be far, far away from where we end up. So above buffer, paste in buff, and we want to put buff right after our SEH buff. And do make sure we keep the C's. So again, that will, since we did the plus equals, it will automatically adjust the links, but we want to make sure that we are writing over the end of the stack, so we cause the exception. So we do need to make sure we pad it. Run it. Guess we need a listener. Just go to root and netcat LVP, so listen verbosely on port 4444, since we did use a reverse shell, and come back over and pass the exception. Again, if we're outside of the debugger, this will automatically happen. I didn't set a breakpoint, so it should just automatically run here. So Shift F9, and now we're running. And if we come back over, we in fact do get our shell here. So everything worked. Alright, so let's open up a new notepad here. And our steps, we still want to get a crash and verify offset to, well, not verify, find offset to SEH with Mona pattern create and link, and do Mona find MSP, look for SEH, verify offset to NSEH, find pop ret with Mona SEH, and of course we can do CPB, bad characters, and then we want, after we do the pop ret, we want to put it in little Indian, of course, and then we want short jump in NSEH over SEH, so that's going to be 0B06 plus 2 bytes of padding. Shellcode after SEH, and be sure to keep the crash. So make sure that whatever's causing the exception is always going to happen. It's a fairly common mistake to have whatever's causing the crash be whatever's going on in the shellcode. So like a read error, trying to read to a bad address or write to a bad address, and then having that place in the attack string be part of the shellcode. So particularly with Metasploit, that's going to regenerate itself every time, and with your polymorphic shellcode, you never know what you're going to get, so you might accidentally get something that's not a bad read or write, and then it won't crash at all. So something to keep in mind. So this is, as far as we're going to go with exploit development, there's certainly much more to learn, but this is just, a basic overview. We've done a lot of using Metasploit, using other people's exploits. I wanted to give you an idea of how these things are found, and how we can write an exploit, so kind of put you on the road towards becoming an exploit developer.